Welcome to lectures 13 and 14. So previously we looked at angular motion and the angular equations of motion. Then we started rigid bodies and studied the concepts of torque, center of mass, and moment of inertia. So torque is the turning effect around a pivot. And a reminder, pivot is a reference point and the torque has to be calculated around the pivot. Okay, so without mentioning a pivot, you cannot calculate torque. And then center of mass is a point where the entire mass seems to be concentrated. Okay, so usually the mass is distributed all over a rigid body, but it is possible to find a single point where the entire mass appears to be concentrated. That point is called the center of mass. And moment of inertia provides resistance to rotation. It depends on the mass of an object and also depends on the mass distribution of the object relative to an axis of rotation. Now let's look at Newton's second law and apply it to rotational dynamics. So this is what we know about Newton's second law for linear motion. The net force acting on an object equals mass multiplied by the acceleration of the object. Okay, so this applies for linear acceleration. Okay, and the force applied is a linear force. Now for rotational motion, we have a similar equation, but we replace some of the terms. We replace the net force with net torque, and replace the mass with moment of inertia, and replace the acceleration with angular acceleration. And we have Newton's second law for rotational dynamics that says net torque equals moment of inertia multiplied by angular acceleration. In other words, the torque that's applied on a rigid object will create angular acceleration in the rigid object. And the amount of angular acceleration created will depend on the moment of inertia of the rigid object around the axis of rotation. Okay, so you can see the similarities here. So force is equivalent to torque in rotational motion, and mass is equivalent to moment of inertia. Or another way to think about this, a force creates acceleration, a torque creates angular acceleration. And then mass resists acceleration, so bigger mass will produce less acceleration for the same force. Similarly, moment of inertia resists angular acceleration. Okay, so you can see the similarities between linear and angular quantities. So let's look at the second law in more detail. So we have alpha, that's the angular acceleration, and we have the equation for alpha in the previous slide. We can rearrange and we get this. Alpha, the angular acceleration, equals torque divided by moment of inertia. Okay, and reminder that a larger moment of inertia means the object is harder to get rotating. Okay, so let's look at these two pictures here. So in both pictures we have a big wheel. So that's like a merry-go-round, for example, and it's fixed at the center. So the axis of rotation passes to the center of the wheel for both the wheels here. And then someone's pushing the wheel in the direction shown in both the pictures with the same force. Okay, and on the wheel there are three people. Okay, however, the difference is that on the picture on the left, the three people are located around the rim of the wheel, and in this other picture, the people are located closer to the center. Okay, so the wheel, the system is rotating around the center. That's the axis of rotation. So in the first picture, the masses are distributed further from the center. They're concentrated around the rim. In the second picture, the masses are concentrated at the center, which means that the first setup will have a larger moment of inertia because the masses are located further. Okay, and it will take more torque to create the same angular acceleration of the first wheel compared to the second wheel. Okay, so in the second wheel, the mass is closer to the axis of rotation, so the moment of inertia of the system is smaller, and then the force applied will create a larger angular acceleration. Okay, so this is how torque, moment of inertia, and angular acceleration related, also expressed as Newton's second law for rotation. So let's do this problem involving torque. We are given a 4-meter long 500 kilogram steel beam. Okay, So we are given the length of the beam and the mass of the beam, and the beam is supported from the right end 1.2 meters away from the right end. So we are trying to calculate the torque around the support. Okay. So notice that here we are trying to calculate the torque, and when we calculate the torque, we have to define a reference point, a pivot. So what pivot are we choosing here? So we can choose any pivot we want, but this question gives us the pivot to use. It gives us the pivot as the support. Okay. So in problems like this, it helps to start by drawing a picture. So this is the picture of the setup. We have the beam and we have the support located 1.2 meters from the right side. Okay. So here we haven't shown any forces yet. So this is the weight of the beam. So we have drawn the weight of the beam right from the middle of the beam. Okay. So we have drawn the weight from the center of mass. And for this beam, the center of mass should be right in the middle because it's an uniform beam. It's the same thickness everywhere, made of the same material. So it should be symmetric in all directions, and the center of mass should be located right in the middle. Okay, so you draw an arrow for the weight from the center of mass. Okay, so this single arrow will represent the weight of the entire bar. Of every little piece in the beam gets represented by this single arrow. Then we look at the pivot here. So we are given the pivot as the support. So the question tells us that to calculate the torque about the support, which means to calculate the torque assuming that the support is the pivot. So the pivot is going to be where the support connects with the beam, so somewhere over here. Okay, now these are what we know. So R is the distance from the pivot to the center of mass. So let's draw R in the picture. So this distance is R. And you can see that R should be equal to 0.8 meters. And I know this because the center of the beam is 2 meters from the right end, and the pivot is 1.2 meters from the right end. So the difference is 2 and minus 1.2, which is 0.8 meters. And the weight of the beam, we know the mass of the beam, and you can multiply by 9.8 to get the weight of the beam. Okay, and then the angle theta. So the angle theta is the angle between the weight, which is the force, okay, and the R vector. Okay, so this angle is the angle theta, and you can see that the weight is pointing straight down, the R is horizontal, so the angle theta has to be equal to 90 degrees. Then, using these quantities, we just use the equation for calculating torque. Torque equals R times force times sine theta. And plug in the numbers here for R, and for the force you plug in the weight and plug in sine of 90 degrees. And the unit of torque is Newton meter. So you do the calculation, you will get negative 3920 Newton meter. Okay. Now, about the sign negative. So when you do the calculation, you don't get a negative sign. But we are still going to put a negative sign for our answer. And why is that? That's because of the direction. Okay, so the positive and negative signs represent the direction of the torque. Okay, so torque can be counterclockwise or clockwise. So a negative sign represents counterclockwise direction, and a positive sign represents clockwise direction. Okay, now in this picture, the support is located to the right of the weight. So the support is located where the triangle here meets the beam, and the weight is pulling the beam downwards on the left side of the support. So imagine that you are pulling down on the beam at the location where the weight is. So you're pulling down the arrow basically. So if you pull down on this arrow, and the beam is rotating, the beam will rotate counterclockwise. Okay, so the beam will rotate in this direction, which is counterclockwise. So this tells us the direction of the torque produced is counterclockwise, so you put a negative sign to represent this direction. Okay. Now, one thing to notice is that this torque is calculated with respect to this pivot here. Okay, so if you move the pivot or if you choose a different pivot, then the torque changes. Okay, and then at the same time, the direction of the torque can also change. So for example, let's say you choose a pivot at the left end of the beam. Okay, you can choose a pivot anywhere. So suppose for some reason you choose a pivot at the left end of the beam, and then you calculate the torque. So you will end up with a clockwise torque. And why is that? So imagine that you fix the left end of the beam. So imagine that you fix a pole where the left end of the beam is, and then you pull down along this arrow for W. Okay, so now your beam is rotating, and you imagine that the beam is fixed at the left end, which means this pulling down on this arrow will make the beam rotate in a clockwise direction. Okay, so in that case, for the same force and for same everything, we would get a different torque because we have chosen a different pivot. Okay, so that's why choosing a pivot is important. Because all right, now using the concept of torque, let's look at the next concept, the concept of static equilibrium. Okay, so what does equilibrium mean? Equilibrium means at rest. Okay, so it's not there is no force acting on it, and there is no torque acting on it, which means that this object is not accelerating and it's not rotating. Okay, and if it's not moving, we say it's a static equilibrium. So that means in addition to having no net force and no net torque, it's also at rest. So let's look at the diagrams given. So here we have a point particle. Okay, and we have two forces acting on the particle in opposite direction, and the forces cancel. So this particle is at equilibrium. Okay, so there is no net force acting on the particle. And now let's look at the next picture here for the block. So again, we have a object. So this time it's a rigid object, and you have two forces acting in opposite directions. Okay, and again the forces cancel. Okay, so there is no net force acting on this object. But let's also look at the other quantity, the net torque. Okay, so these two forces create torques. But if you choose any pivot, for example, you choose the pivot at the center of the box, okay, and then calculate the torque for the two forces, you will get the same torque for both the forces because they're acting like along the direction of each other. Okay, so you draw a straight line from one arrow to the other, and you will see that that arrow passes through the pivot to the center. Okay, all right, so for option B, we have the box which has zero net force and zero net torque acting on it. So this box also is at static equilibrium. Now the third example, we have the same box as before, and we have the same two forces, but let's look at the location of the forces. This time the forces are not lined up, they're not acting along the same straight line. They're acting on, well, one force is acting close to the top and the other force is acting close to the bottom, and they're pointing in opposite direction. So now when you add up the two forces, they will still cancel because one is positive, one's negative. So adding up the forces will give you zero net force. But when you calculate the torques will not cancel. Okay, so think about this. So you choose a pivot for this box. Suppose you choose it right in the middle where the cursor is. So imagine you fix a pole through this middle, and then you pull the box along the arrows. So you pull on both sides along the direction shown by the arrows. The box doesn't stay at rest, the box rotates. The box rotates in a clockwise direction. Okay, so that's because the two forces generate clockwise torques and they don't cancel each other out. Okay, they would have canceled each other out if it were like this in the second picture, if they lay along the same straight line. So these are the conditions that we have for describing something in static equilibrium. The object must have zero net force, which means for the x direction and the y direction separately, when you add up all the forces and the components, you'll get 0. Okay, so if you don't get 0, that means the net force is not 0 and the object is accelerating and it's not at equilibrium. That's one condition. The second condition, you choose any pivot point and then you calculate the torque of all the forces around the pivot point, you should get 0. That would tell us that there is 0 net torque on the object. Okay, so let's again emphasize that when you're calculating the net torque, okay, you can choose any pivot, and no matter where you choose the pivot, you are guaranteed to get 0 torque if an object is at equilibrium. Right, so these are the two conditions of equilibrium, that the sum of all forces acting on the object must be 0 and the sum of all torques acting on the object around any pivot must be 0. So if an object satisfies these two conditions, we say that the object must be in static equilibrium. All right, now let's look at choosing a pivot point. So as we said earlier, a pivot point can be chosen anywhere. It's a reference point. But if you choose the pivot point cleverly, sometimes it will make your calculations easier. Okay. So here let's look at this picture of a hammer. So this hammer, suppose it's a static equilibrium. Okay. And this is what the free body diagram looks like. Okay. So we have the center of mass of the hammer somewhere over here, and you draw the weight from that point. And then suppose the hammer is in contact with the surface here at point B, and there's normal force acting on it. And then at point A, the hammer is also in contact with the surface, so there's normal force acting on it. So these are the three forces acting on the hammer, and it's important that you draw the forces at the correct location. For example, you draw the weight at the center of mass, then you draw forces A and B at the correct locations too, and the correct direction. Okay. So if the hammer is at static equilibrium, you can choose any pivot and calculate the torques for all these forces, then add them up. They are guaranteed to give you 0. Okay, so when an object is in static equilibrium, you can choose any pivot and you will still get 0 torque. So we'll look at examples of how to cleverly choose pivots and to help with our calculations. But nonetheless, again, an emphasis that when an object is at static equilibrium, you can choose any pivot and you're guaranteed to get 0 torque when you add up all the torques correctly around the pivot. Okay, so let's do this example. We have this massless rod. Okay, so let's imagine that this rod doesn't have a mass, or even if it does, let's assume it's negligible compared to all the other masses around, other weights around. And there is a scale that's placed right under the center of mass of the rod. And then on the right side, there's a 1,000 Newton weight pulling the rod down. On the left side, there is a hinge that's holding the rod in place. Okay, so we are trying to calculate the force that's recorded by the scale. So basically we are trying to calculate the normal force of the scale on the rod, because the scale calculates the normal force that it exerts on the rod. So we can draw the forces involved. So let's say the force on the left end, let's call it F left, and the force of the scale, let's call it F scale, that's pointing up, and then the weight of the 1000 Newton, I'll draw an arrow pointing down. Okay, so normal force from the scale points up, the weight of the 1000 Newton points down. But what about F left? How do we know it's pointing up or down? Okay, and suppose we don't know whether it's pointing up or down, we'll just guess that it's pointing down. Okay, so at this point it's just a guess. It could be pointing up or down, but we'll just choose down for now, and then during the calculation we'll be able to determine whether the force is really going up or down. Now let's go back to the problem here, try to figure out what we're calculating. So we are trying to calculate the force from the scale. So we are trying to calculate F scale. Okay, so there are three forces: F left, F scale, and the 1000 Newton. So there are three forces, and we just know the value of one force, the 1000 Newton. We are trying to find the value of the middle force. So the left force, the third force, is what we would like to eliminate from our calculation, because well, we don't know what it is, and we are already left with an unknown of the middle force. So we would like to eliminate the left force from our calculation. So how do you eliminate a force from your calculation? You can do it by choosing a pivot appropriately. So we want to eliminate the F left from our calculation. So we'll choose the pivot exactly where F left is acting. So we'll choose the pivot at this black dot, okay, at the left end. All right, then what? Then we construct something called a torque table. Okay, and what's a torque table? It's this. You have 5 columns. So the first 3 columns are the force, the R value, and the theta. And you have to list down each force in the system. And then you have 2 other columns for calculating. So in the 4th column, you calculate the torque, the magnitude of the torque, using the equation for torque. So that's F times R times sine theta. And the last column is the direction of the torque. It can be clockwise or counterclockwise around the pivot. So that's what you have to determine from your system. So let's fill up the table. So first, in the first column, we list down the 3 forces. So we know one of them, the 1000 Newton, but we don't know the other. So we'll just call them F left and F scale. All right, and then you calculate the R for each force. And what is R? R is the distance of the force from the pivot. Okay, so R is the distance from the pivot to where the force is applied. Now let's start with the first force, F left. So this F left is acting exactly at the pivot, okay, because we chose the pivot exactly at that point. So this means the R value for F left must be 0, okay, and if the R value is 0, then it doesn't matter what the theta is. You can calculate torque. You plug in 0 for the R, you'll get 0 torque. Okay, and the direction doesn't matter either. So basically we are saying if you choose the pivot at the left end, this force on the left does not produce any torque. Okay, and this is how we eliminate the contribution from the force on the left, and then that will help us figure out the other force that we are trying to find. So let's go back to the table, look at the second row. In the second row, we have the second force, F scale. We still don't know what it is. And let's look at the R value. Okay, so F scale is acting at the middle of the rod. And suppose the length of the rod is L. Okay, so the question doesn't give us what the length of the rod is, but let's say the length of the rod is L. So the distance of the middle of the rod from the left end must be half of L. So that's what we plug in for R in the second row. R must be equal to half of L. And then the angle, so here the beam is horizontal, so the R vector is horizontal, and the normal force is pointing straight up, vertical. So if you have a vertical force and a horizontal vector, the angle between them must be 90 degree. Okay, so we plug in 90 degree for the angle for F scale. And then use the equation for torque. So that's force times r times sine theta. So force is F scale. So we plug it in here, and r is L over 2. That also goes in the box. And sine of 90 is just 1. So you put a 1 for the sine of theta, and you get this quantity in the box. And then the direction of the torque. So the pivot is the left end. So imagine that you fix the beam at the left end, then you pull up along the arrow at the middle on the scale. Then the pulling force will make the beam rotate counterclockwise. So the direction of the torque produced is counterclockwise for the F scale force. So we are done with the first two forces. Now let's do the third one. So third one is a 1000 Newton force. We already know what the value of the force is, so I'll plug in 1000. And the R of this force is L, because you can see the pivot is at the left end, and this other force is acting on the opposite end. So the distance between them is the length of the rod, which is L. And the angle between the R vector and the force is again 90 degree, because the beam is horizontal and the force is pointing vertically straight down, so it makes an angle of 90 degree between them. So you calculate torque, so multiply the 1000 with L with sine of 90, you get 1000 L, and this torque is going to be clockwise. So imagine that you fix the left end of the beam, so fix a pole to the left end of the beam, so the left end is fixed, and then you pull down on the right end. Okay, so if you pull down on the right end in the direction of the arrow, that force will make the beam rotate clockwise. So that gives us a clockwise direction for this torque. So what do we have altogether? We have the torques created by the three forces. The force on the left doesn't create any torque because we chose the pivot at the left end, and the other two forces create clockwise and counterclockwise torques of these quantities. Okay, so the next step, you add up all these torques. Okay, so we know that if an object is at equilibrium, like this beam here, when you add up all the torques to find the net torque must be 0. Okay, so we start with this condition. Write down net torque equals 0, and then for the net torque, you plug in all these numbers. Okay, so you plug in 0 for the first torque, then you plug in negative F scale L over 2 for the second torque, and remember, counterclockwise is represented by a negative sign, and clockwise is represented by a positive sign. That is just convention. So you plug in negative of the torque for the second force, and you plug in a positive torque for the third force. So you get an equation where the unknown is F scale. Okay, so rearrange the equation, and then you can see that the L's cancel out, and then you can calculate the F scale. You get 2000 newtons. So that's the reading on the scale. That's how much force the scale applies on the beam to keep it at equilibrium. So important to notice that here we needed to eliminate F left because there were two forces and we were trying to find the middle force. So we eliminate the left force. And how do we do that? By choosing the pivot at the left force. So if you choose the pivot where the left force is acting, it's the same as eliminating any torque generated by this force. And then in the torque table, you'll end up with 0 torque for the contribution from that force, and then you're left with the other force, that's the only unknown. Then you can use the equilibrium condition, setting net torque equal to 0, and then follow the steps and calculate the unknown force. All right, so some general steps here. Okay, so usually the first step is to determine whether your system is in static equilibrium. Okay, the question might tell you, or even if it doesn't tell you explicitly, it might give you information to figure it out. And then step 2, usually it's a good idea to draw a free body diagram where you draw all the forces and draw the forces at the correct locations. Okay, and then you can create a torque table like we did. Well, sorry, you can choose a pivot first and then create a torque table, and then look at the conditions for equilibrium, whether the net torque is 0 or whether net force is 0 or both. And using these conditions like we did in the previous slide, you can set up an equation and solve for the unknown force. So let's do some more problems. So this is what we're given. We have two children balanced on a seesaw and the mass of the seesaw is negligible. So one child has a mass of 26 kilogram and sits 1.6 meters from the pivot. Okay. And the other child has a mass of 32 kilograms and we are trying to calculate how far she is from the pivot. So let's draw a picture. Okay. So we can assume that the pivot is somewhere here, I guess close to the middle. Okay. And we have the two kids here and their weights are pointing straight down, and there's a force from the pivot as well pointing straight up from the middle. Okay. So on the left, the weight of child 1, so that's W1, creates a counterclockwise torque. Okay, so it's trying to rotate the seesaw counterclockwise. And the weight of the other child does the opposite. It creates a clockwise torque. Okay. And the question says the children are balanced. Now what does that mean? That means the system is at static equilibrium. Alright, so if the system is a static equilibrium, it means that the torque generated by the two weights must cancel each other. Okay, so net torque must be 0. Okay, so you can choose a pivot. Now where would you choose a pivot? So it makes sense to choose a pivot where the unknown force is. So here we don't know what FP is, it's an unknown force, so we might as well choose the pivot exactly where the FP acts from. So that way it will eliminate the contribution for of FP. Okay, so these are the list of information that we have. We have the weight of child 1, so you can do mass times G, you get 254.8 newtons, and R1 is the distance of the child from the pivot, it's also given 1.6 meter. And then you can calculate weight 2 as well, you get a slightly bigger weight, and R2 is what we are trying to find. And FP, the force from the pivot, is something that we don't know. And RP is going to be 0, that's the distance of the pivot from the pivot, which must be 0. And the angles must be 90 degree here because the beam is horizontal and the forces are vertical. So the angle between them must be 90 degree. So we know all this, we can take them to the next slide. Alright, so we do this here. We said the net torque must be 0. So sum of torques must be 0. And there are three forces, so there can be three torques. Let's call them torque 1, torque 2, and torque P for W1, W2, and FP. So these three forces will generate these three torques. And then you plug in the equations for the torques here. So torques 1, 2, and P. Plug in the equations. So you can see that you need to know the forces, the R, the angles, but we have already calculated them in the previous slide. Okay, so we know that RP must be 0. So because the pivot is where the FP is acting from, so FP is exactly on the pivot, so the R must be 0. So basically the third term goes away, it becomes 0. And then for the other terms you plug in the numbers that you know. Okay, so W1 is 254.8 newtons, R1 is 1.6 meters, W2 is 313.6 newton, and R2 is what we're trying to find. Okay, so plug in the numbers and you have a single unknown R2. So rearrange the equation and you get R2 of 1.3 meters. So the calculation would give you a negative value. That's because we didn't account for direction of the torque up here. Okay, so strictly speaking, W2 is producing a clockwise torque and W1 is a counterclockwise torque. So W1 should have a negative sign, but we haven't accounted for it in the steps, so we end up with a negative sign for R2. But the question is asking for the value of R2, just how far she is, so you just choose a positive value. Okay, so negative sign doesn't matter because the question is just asking for how far and not the direction or anything. Then let's move on to part B. So part B is asking about FP. Okay, so we know what W1 is, we know what W2 is. So what should FP be so that it balances the two weights? Okay, so for this we can use the other condition of equilibrium, that the sum of all forces must be 0. Okay, and what are the forces here? W1, W2, and FP. So you add up W1, W2, and FP, set them equal to 0. Okay, so just like that, and then plug in the values. Now for W1 and 2, you can see we're plugging in negative values. And why is that? Because the weight is pointing down. So remember, pointing down means negative, pointing up means positive. So you plug in negative values for the W's, then FP is what you're solving for. Rearrange and solve, we get force equals 568.4 newtons. So basically the force of the pivot is the same as the combined weight of the people here, okay? So, and that's not surprising because however much weight is trying to pull the system down, the pivot has to counter it by applying the same force in the opposite direction. So that's what we get for the pivot force. Let's look at this other example. We have a teeter-totter of a certain length of 5.2 meters and a mass of 26 kilogram, and the pivot is at the center. So the question tells us where to choose the pivot. We have an 18 kilogram child sitting on one end, and the parent is pushing with a force of 210 newtons somewhere else. We are trying to figure out the location where the parent should apply a force to keep the teeter-totter level, which means that the teeter-totter should be horizontal or at static equilibrium, okay? So you can draw a picture for this, and when you have drawn the picture, you can construct a torque table. So this is what you'll end up with, that you can choose the pivot at the center, okay? And the center of mass of the teeter-totter must be at the center as well, okay, because it's uniform. So the R value of the center of mass must be 0 because it's the same as the pivot, okay? And then there is a force at the pivot, the normal force, okay, which should also have R value of 0 because, we are choosing the pivot where the force is acting at. Then we have the R value of the child that's given, 2.6 meters from the pivot, okay. So it's not given directly, but it tells you the length of the beam is 5.2 meters, and the pivot is at the center, and the child is at one end. So distance from the end to the center must be half of the length of the beam. So half of 5.2 is 2.6. And then the R value of the parent is what we're trying to find. Okay, so using these values for R, let's move on to the next line and use the condition for equilibrium. So this condition says the sum of all torques must be 0. And what are the torques here? So there are 4 forces: the weight, the force of the pivot, the weight of the child, and the force from the parent. Okay, so the first one is the weight of the beam. Okay, and then we have the weight of the child separately. So you add up the torques from the 4 forces. Let's call them torque of center of gravity plus torque of pivot plus torque of child plus torque of parent. Set them equal to 0. Okay. Now we know directly that the torque from the center of gravity of the beam must be 0 because we chose the pivot exactly where the force is acting from, and same with the torque from the pivot force because normal force from the pivot is also acting exactly where the pivot is. And then the torque generated by the weight of the child must be the weight multiplied by the R value, okay? And for the parent, okay, we have multiplied the force with the R parent. And remember to put a negative sign for one of the torques, okay? So we have the torque of the child and the torque of the parent that are not 0, and they're acting in opposite direction. One's clockwise, one's counterclockwise. The question doesn't tell us which is which, so just choose one to be positive, one to be negative, okay? And it doesn't matter which you choose to be positive or negative, you'll get the same answer. So in this equation, you can rearrange, solve for the R parent, and that's equal to mg times R value of the child divided by 210. And then you plug in the R value of the child, that's 2.6 meters, into the equation and calculate, you get 2.18 meters. So that's the answer we are looking for. The parent should be pushing 2.1 meters away from the pivot with a force of 210 newtons to keep the teeter-totter at equilibrium. Next problem. You can see in the picture that this person's holding a pole of 5 kilogram horizontally. So with his 2 hands, okay, and the hands are 0.9 meters apart, and the center of gravity of the pole is right in between the hands, 0.45 meters from the left hand. So So we are trying to calculate the FR, that's the force exerted by the right hand. And then for part B, we calculate FL, the force exerted by the left hand. Okay, and this is what the free body diagram looks like. So we have the two forces from the hands going up and the weight pointing straight down from the center of mass right in the middle. Okay, so these are what we know. The weight of the beam is mg, so it's 5 kilograms times 9.8 newtons gives you 49 newtons. And then Rw is the distance of the weight from the pivot. Okay, and then where do we choose the pivot? You choose the pivot at the left end. Okay, so why do you choose the pivot at the left hand and not at the right hand or the center of gravity? That's because you're trying to find the force on the right hand. You're trying to find Fr. Okay, so again back to the picture here. There are three forces, Fr and Fl, which we do not know, and there's W, which we do know. Okay, so there are two unknown forces, Fl and Fr, and you're trying to find Fr first. So you want to eliminate the contribution from Fl, and you do that by choosing the pivot at Fl. Okay, so that's why you choose the pivot at the left hand to find the force Fr. So if you choose the pivot at the left hand, then the distance from the center to the pivot is 0.45 meters. It's given in the question. And then this automatically means the R value of the left hand must be 0 because the pivot is at the left hand, and the R value of the right hand must be 0.9 meters. So the distance from the right to the left hand is 0.9 meters. So this is a simplified picture of the free body diagram with all the distances marked and the known weights marked, and the pivot is also marked at the left hand. Okay. Then choosing the pivot at the left hand, you can construct a torque table. So like this, you list down the three forces in the first column, then list down the R values in the second column. So you can use the same R values as are listed over here in the picture, 0.45, 0.9, and 0. Then the angle is 90 degrees because the beam is horizontal and the forces are vertical. Then you calculate the torque. So multiply the force with the R with the sign of the angle. So for the FL, you get 0 torque because it's at the pivot. And then for the other forces, you get counterclockwise and clockwise torque. Okay. So for the weight around this pivot on the left hand, the weight creates a counterclockwise torque. And then the Fr will produce a clockwise torque. Okay. And these are what you end up in the columns, 22.05 for the counterclockwise torque and 0.9 times Fr for the clockwise torque. So now that you have all the torques, you add them up and set them equal to 0. So use the equilibrium condition. Net torque equals 0, and net torque is just all these torques added together with the correct signs. Okay. So counterclockwise is negative, so you put a negative 22.05 in the calculation. Then clockwise is positive, you put 0.9 Fr in the equation. Then rearrange, solve for Fr, you get 24.5 newtons. Okay, so that's how much force is exerted by the right hand, 24.5 newtons. So that's really half of the weight. And then part B wants us to find FL. Okay, so the total downward force is 49 Newton. So the weight of 49 Newton pulls the pole downwards, and the right hand pushes it up with 24.5 Newton, so half the force. So this other half, so the other force on the other hand must account for the other half of the force. So you can also calculate by using the net force condition. So you set the net force equal to 0, and then for the net force, plug in all these forces. Fr and Fl were pointing up, so you put them positive, and put negative W for the weight pointing down. Then plug in the numbers and solve for FL, you get 24.5 newtons. So it's the same as Fr. So in this case, both the hands apply the same force. That is because the weight is located at the middle of the two forces. Okay? So we'll see in the next example that if the weight is not exact at the middle, if it's closer to one hand than the other, then the hand that's closer to will exert a bigger force. Okay, so here's the example. We have the same setup as before with the pole of 5 kilogram held by hands 0.9 meters apart, but this time the center of gravity is 0.6 meters from the left hand. So it's further from the left hand and closer to the right hand, is 0.3 meters from the right hand. And we are trying to calculate FR and FL like before. So again, we start by choosing the pivot at the left hand, then fill up the quantities. So we have the same weight of the pole, RW becomes 0.6, RR is still 0.9. And we'll use them to construct a torque table. Okay, so this is our diagram here. So you can see the weight is shifted away from the middle, is closer to the right hand. It's like 0.3 meters from the right hand and 0.6 meters from the left hand. Then choosing the pivot at the left hand, construct a torque table like this. So list down the three forces and the R values, and FL will still have a R value of 0, and the weight will have a R value of 0.6, and FR will have a R value of 0.9 like before, and the angle is 90 degree. You calculate torque by multiplying the force with the R and then the sine of the angle. So you will get 29.4 counterclockwise for the weight and 0.9 FR clockwise for the FR force. Now use the equilibrium condition, add up all these torques with the correct signs, set them equal to 0. So you have 0, then negative 29.4, positive 0.94, 0.9 FR. Rearrange, solve for FR, you get 32.7 newtons. So this time FR is more than half the weight, okay, because the weight is located closer to FR than FL. So FR has to be bigger. And then to find FL, you just find the difference. So FR and FL added together must equal the weight. So FR is 32.7, the weight is 49, so FL must be 16.3 to make up the difference. So this time FL, you can see, is half of FR. Okay, so it's 32.7 versus 16.3. And that's because RL is double of RR. Okay, so the further the weight is from the force applied, the smaller the force is. Okay, and this also applies when two people are trying to lift a heavy object. The person who who holds closer to the weight, closer to the center of mass, will have to apply a bigger force than the other person. Okay, so the further you hold from the center of mass, the smaller force you have to apply. But eventually, if you want to lift the object, you have to apply a total force that's equal to the weight of the object. It can be less, and if it's more, then you have motion. It won't be at equilibrium. Now, this problem here, we have construction worker of 80 kilogram sitting on this beam, and the beam is connected to a wall. So first by a cable that's connected at 30 degrees to the right side of the beam, and then also it's fixed at the wall. So there's force from the wall holding it back, maybe like nuts and bolts connecting the beam to the wall. So we know the mass of the worker, we know how far the worker is located from the wall, and we know the length of the beam, and we also know the mass of the beam. Okay, and the cable has a rating of 15,000 newtons. So if the tension in the cable exceeds 15,000 newton, then it could break. Okay, so the tension has to be less than 15,000 newton. So the question is asking, should the worker be worried that the tension has exceeded 15,000 newtons? So let's calculate the tension in the cable. So let's draw the forces involved, and there are lots of them. So we have the weight of the worker, which can be calculated, multiply the mass with G. The weight of the beam, which can also be calculated, multiply the mass of the beam with 9.8. And then we have tension in the string, which we don't know, but we know that it's acting in this direction, shown by the arrow. And we also have a force from the wall. Now, the force from the wall, we don't know which direction it's acting. So it can be acting in the direction that I've shown. It can be acting in a different direction. We don't know. So I'll just draw this arrow for the force of the wall for now. And later on, we'll calculate what this force is. But for now, let's just put an arrow that's acting at point A, so the left end of the beam. And let's call it the force of the wall. So using this free body diagram, we choose a pivot. So where do we choose a pivot? Okay, so let's look at the forces. There are 4 forces, 2 weights, the tension and the force of the wall. and we are trying to calculate the tension. That means you want to eliminate the other force, the force of the wall. That means you have to choose a pivot where the force of the wall is applied. That's at point A. Okay, so you choose a pivot at point A, and then calculate these quantities. So the weight of the beam is mass times G. So mass is 150 kilograms, gives you 1470 newtons. The R beam is the distance of the center of mass of the beam from the left end of the wall, which should be half the length of the beam. That's 3 meters. And the angle is 90 degrees because the beam is horizontal, the weight is vertical. Then for the worker, repeat the process with the mass of the worker to get 784 newtons, and the distance of the worker from the wall is given already. You can calculate from the picture. It's 6 meters minus the 2 meters on the right side. That gives you 4 meters from the left end to the worker. And the tension in the cable, we don't know what it is, but we know the R value is 6 meters because the tension is acting exactly at point B, at the opposite end. And the length of the beam is 6 meters. And the angle for this force, for the tension, is not going to be 90 degrees, it's going to be 30 degrees. Because you can see that the tension is acting this way, and the beam is horizontal. So the angle between the beam and the arrow is 30 degrees. And the force of the wall, we don't know what it is, but we know that the R value of the wall must be 0 because the pivot is exactly at point A where the force is applied. So the torque of the wall is going to be 0. So now we use the equilibrium condition. We add up all the torques. So there are 4 forces and they produce 4 torques. So let's call them torque of the beam plus torque of the worker plus torque of tension plus torque of the wall. And then you plug in the numbers, plug in the expressions for the torque of the beam and for the worker. You multiply the weight with the R value with the sign of the angle. And then for the torque of the tension, you multiply the T with the R value and the sign of 30. And the torque of the wall is already 0, so you can just put a 0 here. And then next line, you plug in all these numbers. So we have calculated these values in the previous slide, so plug them all in. And the only unknown is the tension T, okay? And also remember to plug in the proper signs, because see, both the weights are creating clockwise torques around point A, but the tension is doing the opposite. It's creating a counterclockwise torque around point A. So for the torque of the tension, we put a negative sign. So going back to the calculation, so the only unknown is the T. So you rearrange the equation and solve for T. You get 2515 newtons, which is considerably less than the cable rating, 15,000 newtons. So the worker doesn't have to be worried about the cable breaking. Now for part B. So we found the tension, and we can find the force of the wall that's acting on the beam. Now we know what the direction of the tension is. It's along the cable, but we don't know what the direction of the force of the wall is. It can be horizontal, vertical, diagonal, at some angle, we don't know. So we'll start by assuming that this force of the wall has a horizontal component and a vertical component. Okay, so that's what we start with this assumption, because it could have both components. So how do we find the horizontal vertical components of the force of the wall? You use the other condition for equilibrium, that the sum of all forces must be 0, okay? Which means the sum of all forces in the x direction must be 0, and the sum of all forces in the y direction must be 0, okay? So let's look at this picture here. So the 2 weights are pointing in the y direction. They're pointing straight down, negative y direction. But the tension is pointing at an angle. So the tension has both x and y components, okay? So in the x direction, we have the force from the tension. Let's call it Tx, the x component of the force from the tension. And that's not all. We also have the x component of the force from the wall. So let's call it F wall x. And they're acting in opposite direction. So the x component of the tension is pointing to the left. The x component of the force of the wall is pointing to the right. So in the x direction, there are 2 forces, the x components of tension and force of the wall in opposite direction. So in the x direction, this is what we write down for the net force. the net force in the x direction is F wall x minus Tx, and that should be equal to 0 because we know the net force should be equal to 0. And we are trying to solve for F wall x, and for the x component of the tension we use trigonometry. We use T cosine theta, cosine the angle. Okay, so the angle here is 30 degrees from the x-axis, from the beam, so you do T cosine 30. Then you plug in the value of T from the previous slide. Okay, that's 2515 newtons. Plug in cosine 30, calculate, you get 2178 newtons. So the wall exerts a force of 2178 newtons horizontally on the beam. Okay, so that's the x component of the force of the wall on the beam, so the horizontal component. Now let's look at the y direction. So in the y direction there are two weights pointing down, but there are also the components from the tension and the force of the wall. So we now calculate the y component of the tension. Let's call it Ty, and that's going to be tension multiplied by sine of 30 degrees. It's going to be pointing straight up. Similarly, for the force of the wall, so suppose it is the y component, let's call it force of the wall y. So altogether we have four forces pointing in the y direction, the two weights pointing down and the two components of the tension and force of the wall pointing up. So this is how we write it. The net force in the y direction is this force, the four forces added. So we plug in F wall y plus Ty. So these are the two components and they're both pointing up, so they're both positive. Then you subtract the weight of the beam and the worker because they're pointing down. Okay, so now rearrange the equation, solve for F wall y. So we get this here. So for Ty, you plug in T times sine of 30. The weight of the beam is 1470 newtons. The weight of the worker is 784 newtons. We already calculated them. And the calculation gives you 996 newtons. Okay, so the wall exerts a horizontal force of 2178 newtons on the beam, and also exerts a vertical force of 996 newtons pointing up on the beam. All right, problem 6. Let's look at the human arm. Okay, so we have the upper arm and the lower arm, and suppose the lower arm is supported by forces from the bicep and the elbow muscles. So there are two muscles that connect the upper and the lower arm. Okay, and the elbow is located at the end of the lower arm, and the bicep muscle connects very close to the elbow. Not exactly at the elbow, but pretty close. Now, suppose the upper arm is held vertical and the lower arm is held horizontally at equilibrium. Okay, kind of like this. Okay, so you hold your arm like this, and these are what the forces look like. So we have the elbow force pushing the lower arm down, and the bicep force pushing the lower arm up. And we also have the weight of the lower arm that's acting from the center of mass. Okay, now let's use some numbers. Suppose the mass of the lower arm is 5 kilogram and its center of mass is located 0.25 meters from the elbow. Okay, and the bicep connects 0.02 meters from the elbow. So the bicep is pretty close to the elbow, like 2 centimeters, but the center of mass of the lower arm is much further, it's 25 centimeters. Okay, so we know what the weight of the lower arm is. You can multiply the mass with 9.8, you get 49 newtons. But then there are two other forces, the F bicep and the F elbow, which we don't know. So let's calculate these two forces. All right, so there are two unknown forces. So let's start by calculating the bicep force. Let's calculate FB. So if you want to calculate FB, you want to eliminate FE. So choose the pivot at the elbow. So the FE has its contribution eliminated. So choosing the pivot at the elbow, these are what you know. That the weight is 49 newtons, its R value is 0.25 meters, already given in the question. And the angle must be 90 degrees because the arm is horizontal, the weight is vertical. FB, we don't know what it is, but we know that R value must be 0.02 meters, again given in the question. And theta must be 90 degrees. And for FE, we don't know what it is, but we know the R value must be 0 because the pivot is exactly where FE is pointing. All right, so these are what we have, the values that we've derived. Now we use the conditions for equilibrium. Let's use the condition for torque. that sum of all torques must be 0. Okay, and these are the three torques for the three forces. So we have torque from the bicep force, the elbow force, and the weight. So let's call them torque B plus torque W plus torque E equal to 0. And if the elbow is the pivot, so the weight will be trying to turn the lower arm clockwise. Okay, and the bicep force will try to turn the lower arm counterclockwise. So the bicep force creates negative torque, counterclockwise torque. Okay. So for the bicep for torque, plug in negative force times R times sine of 90. For the weight, torque of the weight, plug in the weight plus weight times R value times sine of 90, and the torque of the elbow is 0. Okay, then plug in the numbers. So you're solving for FB and plug in the values for RB and W and RW in the next line here. Rearrange and solve for FB. You get FB equals 612.5 newtons. So you can see that the weight is 49 newtons for the lower arm, but the bicep has to exert a lot bigger force to keep the arm horizontal. And that is because the bicep is located much closer to the elbow than the center of mass. Okay, so to make up for the smaller distance, the bicep force has to be much bigger in magnitude, okay, to compensate for the torque. Now for the next part, let's solve for FE, the force of the elbow. So we know the force of the bicep and the weight. So we know two forces, and the third one must balance the other two. Okay, so we use the equation for force equilibrium. Okay, so that the sum of forces must be 0. All right, so we have three forces, FB plus W plus FE, and set them equal to 0. So FB we already solved in the previous slide, 612.5 newtons. Weight is negative 49. Again, negative means the weight is pointing down. And then we are left with FE, okay, the unknown. So again, move the FE to one side, then do the calculation. You get negative 563.5 newtons. So negative sign means the FE is pointing downwards, which makes sense because the FE and the weight together must add up to the FB. So the forces pointing up must cancel the forces pointing down. And just like FB, FE is a lot bigger than the weight of the arm. That's because FE has to counter some of the force from FB. So really, when you're holding your arm horizontal, your muscles are applying a lot bigger force than the weight of the lower arm itself. Now, we are looking at problem involving a wheel and an axle. So we're going to apply torque and static equilibrium to this problem. So we have this setup, a large wheel of radius 10 centimeter connected to an axle of radius 4 centimeters. Okay, so we are measuring the radius from the center to the edge, and both the wheel and the cylinder have the same center. Okay. Then you apply a force of 12 newtons on the wheel. Okay, and you want to apply a force on the axle in the opposite direction to keep it at equilibrium. So how much force should you apply on the axle? Okay, so here the force that you apply on the wheel and the axle will create torques. Okay, and to keep the system at equilibrium, the torques must cancel each other. So let's draw a picture. So this is our picture here, simplified, showing you the forces. So we have the wheel, the blue circle, and the axle, the green circle, with a smaller radius. And you're applying a force on the wheel, suppose in this direction, and this force is 12 newtons. And you want to apply a force on the axle to keep this system at equilibrium. So basically, to prevent the system from turning, you have to apply force on the axle. Okay. Now, let's think of torque. The force on the wheel generates some torque. And to calculate the torque, you multiply the force with the R value of the wheel and then the sine of the angle. Similarly, the force on the axle generates a torque, and to calculate the torque, you factor in the force of the axle and the radius of the axle. Okay, and and in both these cases, when we calculate the torques, it's easier to calculate the torque around the pivot at the center, okay? Because um, if you choose the pivot at the center, then the radius just becomes um, the same as the R value. So the radius of the wheel is the same as the R value for the F wheel, and the radius of the axle is the R value for the force of the axle, okay? So choose the pivot at the center, and these are what we have. So force of the wheel is 12 newtons given, and the radius of the wheel is 0.1 meter. So it's given 10 centimeters, you have to convert to 0.1 meter. And the angle must be 90 degree because the force is tangential and the radius is the radius, and the radius must be perpendicular to the tangent, okay? And the force of the axle is what we're trying to find, and the radius of the axle is 4 centimeters, which is 0.04 meter, and theta is 90. So then you do the sum of torques, okay? So you add the two torques and set it equal to 0. And for the two torques, you use the usual equation, force multiplied by R value multiplied by sine of 90. So, and you do it for both the wheel and the axle, and for one of the quantities you have to put a negative sign because one torque is clockwise and the other is counterclockwise. The question doesn't tell us which is which, so just pick one. Alright, so plug in the numbers, do the calculation, you will see the only unknown is the force of the axle. And when you solve for it, you get 30 newtons. So as expected, you have to apply a bigger force on the axle to counter the torque from the force of the wheel, okay? So the force of the wheel acts over a bigger distance, a bigger radius. So to counter the torque produced, you have to apply a bigger force on the small radius, okay? So there's a relationship between force and distance you can see, which we'll encounter when we are dealing with torque and the effect of force over distance. Okay, so this is something important about the relationship between force and distance. Now, in the example before, talking about the axle and the wheel, so you can see that it's possible to multiply force. So it's possible to generate a bigger force by applying a smaller force, provided that you apply it over a different distance, okay? So by changing the distance, you're able to multiply a force. And that's the same principle used in other systems as well. So we talked about the wheel and axle that can multiply a force. So you can generate a bigger force on the wheel. You can generate a bigger force on the axle by applying a smaller force on the wheel. And also in a crowbar. So a crowbar is used to lift something, like pry open a door, for example. So a crowbar consists of a long end and a short end. And when you apply a force on the long end, it produces a much bigger force on the short end. And again, that's because of the distances involved. So there's a pivot point close to the short end, and the distance where you apply the force on the long end is a lot bigger than the resultant force on the short end. So it results eventually end up with much bigger force generated on the short end, okay? So that's another example of force multiplication. And then we have car jacks. So if you're changing a flat tire, you'd want to lift your car. Now, of course, the weight of the car is pretty big, but you're still able to lift it using a car jack. And you do that by applying a small force on the car jack handle, but you turn it over a big distance. So every time you turn the handle, you're covering a big distance around the circumference. And on the other side, it produces a big force on the car, but lifts it a small distance, okay? So you can see the relationship here. You're providing a small force over a big distance, and you generate a big force over a small distance, okay? So we relate the force and the distance by this relationship here, that force is inversely proportional to distance. So this symbol is proportional. So when it's proportional to 1 over r, we say that force and this r are inversely proportional. And this is the same as saying that if you multiply the one force with the corresponding r, is the same as the value of the other force multiplied with the other value of r, okay? So there is a force-distance relationship, and when we study work and energy, you will see this again.